if you have like a nucleus like hydrogen that just has one positive charge, it's conceivable that hydrogen could have as many as like 2 electrons around it that would be in a 1s orbital, and that 1s orbital around hydrogen is going to be reasonably low energy. But if you start to populate more electrons around that hydrogen nucleus, you're going to have electrons in a 2s orbital, and that's going to be further out. Like on average, those electrons will be further out from the nucleus, and it's kind of hard for just a +1 charge to keep those electrons around it. So if you live on Earth, as we do, and there's lots of places for electrons to go, lots of nuclei competing for electrons, a third electron around a hydrogen nucleus is not going to survive for very long. It's going to get oxidized by basically anything out there. Maybe in space, something like that might survive. I don't know, but here on Earth, not so much. We got a very oxidizing atmosphere, and something like that would easily oxidize oxygen gas or nitrogen gas, etc. So bottom line, it sounds like, I'm going somewhere with this. So bottom line, we have in our building up of molecules and Lewis structures, we have this idea of an octet rule or a duet rule. And this comes from just what orbitals are available to be populated. So hydrogen and helium, they only really fill up 2 electrons, right? If you look at the periodic table, you can see that, look, we have 1, 2 electrons possible to fill up here. On the second row, you have as many as 8 valence electrons that could be populated around a nucleus, right? It gets a little trickier after the second row. I'll show you why it's trickier right now. Okay, so for that first row of elements, they fill the 1s orbital. For the second row, there's 2s and 2p, and that's when the p block stops, when these p are filled up. And then for the next elements, the third row, they fill the 3s and the 3p, but it's conceivable in bonding that the elements in that third row could somehow start accessing the 3d orbital somehow. So there's actually a little bit of controversy around this. There are some people that don't like to think about this actually happening. They think about things in terms of, I think, what's called natural resonance, something like that, where they don't actually view this as being real, but for our purposes, we'll use this. So bottom line is that in that first row, those first row elements, they can get... Wow, I just did a terrible color coding on this, right? I made the wrong color coding, terrible stuff. Hang on. Let me fix this stuff. So the takeaway for bonding, at least for our purposes here, is that in that first row, you're stuck at having a maximum of 2 electrons in your valence electron set. So if you're hydrogen or helium, you can't have more than 2 electrons, two valence electrons. If you're in the second row, you're stuck at the octet rule. So that means that your valence electrons, not your total electron count, but just your valence electrons, you're stuck with being surrounded at a max of 8 electrons. And then below that, third row and downward, you could actually think about filling up a D set if you really needed to, or if it was kind of called for by the molecular formula. So you don't necessarily stop at 8. If there needs to be more bonding or more electrons to be put around things, you could have a third row element with more than 8 electrons around it, and you would not be marked wrong necessarily based on that. If you come up with something that's ridiculous in other ways, you could easily be marked wrong, but that's possible for third row. This is a big deal. It's a big deal to my wife because as an organic chemistry professor, she gets very angry when people do this. If they draw a carbon... See, how did you do that, Paint? There we go. If you draw a carbon with 5 bonds to it, my wife gets very angry because in the second row it doesn't have enough orbitals in its valence set. It doesn't have 5 valence orbitals. It just has 4. So this is wrong. Like, no. Like sad face. So don't do this. So let's do some more talking about how we can use this stuff. Come on. Well, I guess I'm just going to go through this stuff. Since I'm going to try to do like complete tutorials of stuff, let me kind of get to another idea. So I hope you guys can kind of see this. Yeah, that's not bad. So believe it or not, the number of places that you put electrons around a central atom can help you predict the bond angle of that central atom. So if you have 2 bonds, like 2 separate bonds, or if you have like a lone pair of electrons and another bond, that's a linear geometry. So between the 2 things that are bonded to the central atom, there's going to be a 180-degree angle. If you have 3 things, or 3 places where you find electrons around a central atom, so that could be like a lone pair here and 2 bonded elements here and here, or you could have 3 bonded elements around the central atom, whatever. 3 things, 3 places around the central atoms where you find electrons, that's going to give you a parent geometry of trigonal planar. So the parent geometry says there's going to be an 120-degree angle between everything in that, everything that is bonded to that central atom. And you might actually say, well, if there's one of these that's not a element but just a lone pair occupying space, there would still be that roughly 120-degree angle. And you would call the molecule that doesn't have that third substituent but just has a lone pair there as being bent. So the parent geometry is still trigonal planar. That's where the 120 degrees comes from. But you remove one of the pieces. If this is like a Mr. Potato Head or a Lego set, you just remove one of the Legos, and the think of it as being an empty space occupied by a lone pair, and it still forces the geometry of about 120 degrees between the remaining substituents. And instead of calling it trigonal planar, you might call the geometry bent. If you have 4 things surrounding a central atom, the parent geometry will be tetrahedral. And the angle between the different substituents that are bonded to the central atom are going to have a 109.5 degree angle between them. If all 4 of the things bonded to this, or all of the 4 places that electrons are found around the central atom, are actually bonds, then you would call it tetrahedral. It's a tetrahedron. That's it. If you ended up having 3 of these things be bonded elements, and the 4th place being occupied by just like a lone pair of electrons or a single electron in an orbital, like a radical as it's called, this would still be a roughly 109-degree angle between all these bonds, but the geometry, instead of calling it tetrahedral, you might call it Trigonal Pyramidal. And it's like a tripod. I mean, that's what it looks like. So the central atom's kind of like the vertex of the tripod, or the place where you put the camera, and then the 3 legs of the camera are the actual bonded elements, and the top of the camera where there's nothing, but there could have been like a 4th leg, it wouldn't really be a leg, like a flag or something at the top, that's just occupied by electrons, not by atoms at all, not by bonded elements. And so instead of just calling it tetrahedral, we might call it Trigonal Pyramidal. If we had 2 of these occupied by lone pairs or just or radicals, we would call this overall geometry with just 2 atoms bonded to the central atom bent. So it would be called a bent geometry, even though the parent geometry is called tetrahedral, and the bent just simply signifies that there's not going to be any sort of atoms protruding from the central atom and two of these sites that could have been occupied by an element. There are two more that I don't have on this slide, so I will now produce them for you. So we have for number of places that you find electrons, we had 1, 2, 3, 4, 5, 6, and that's good enough for me. And for 1, it's going to be linear. And for 2, it's going to be linear. And for 3, it's going to be Trigonal Planar. And for 4, it's going to be tetrahedral. And for 5, should probably make this way bigger. For 5, it's going to be Trigonal Bipyramidal. And for 6, it's going to be octahedral. And let's see. 180, not really sure about that one. 180, 120. These are just the bond angles. 109.5 for tetrahedral. Trigonal bipyramidal. Let me get rid of that space. All right. Trigonal bipyramidal will be 90 and 120. There's two different angles there. And for octahedral, everything's 90. Okay, so I'll start drawing some of these and talking about them. Let's do that. So this is number of places you find electrons. And this is the parent geometry. And this is the bond angle associated with that parent geometry. So here's carbon monoxide. Okay. So if I look at this carbon, I see that there's two places I find electrons. There is a lone pair here, and there's some multiple bonding here. So that's two places. Guess what? This is kind of a philosophical question, so I don't know, whether or not I want to think about this as being linear, because it's not that exciting. But this is going to be linear because it has two elements in it, regardless of what's happening. 2 points will make a straight line, regardless of where these electrons might be. It's not going to matter because there's no substituent there to put the to manifest that bond angle. So, in a sense, sometimes it's philosophical. That's why I put a question mark here for 1 or for 2. Let's see. So if I have something else that's linear, beryllium hydride. Here I see that there's two places I find electrons. In this bond and this bond, two places I find electrons around the central atom. So this is going to have an overall 180-degree angle. Okay? I could have, instead of hydrogen, I could have fluorine. And fluorine's going to have more electrons around it. I'll show you guys how to do this in a moment. But I'm just covering all my bases on how to think about this stuff. So here's like a different molecule with a fluorine instead of a hydride on this side. It won't change the overall geometry of the central atom because these lone pairs of electrons aren't on the beryllium. So they're not going to change the number of pairs of or number of places I find electrons around the beryllium. I'm only concerned about the coordination sphere, things that are bonded to the beryllium, things that are occupying orbitals in that beryllium, not things that are happening elsewhere in the molecule. So this doesn't change it. So that would still be linear. It would be 180 degrees. We talked about trigonal planar. Here's an example of trigonal planar. So this is kind of a lie, kind of, because this doesn't actually exist like this in real life, but we'll go with it for pedagogical purposes. So it's okay to lie if you're a teacher. Yes. So, how many places do I find electrons around this boron? 3 places, right? 3 bonds, 3 different places. Okay. So, I look at my chart here. This is going to be a trigonal planar geometry. The bond angle between each of these, like HBH angles, that's going to be 120 degrees for all of these. So it's trigonal planar. Hooray. If I had instead ionic fragment that looked like this, like if I somehow was able to make a boride, so this have an overall minus charge. If I had a boride ion, how many places do I find electrons around this boron? The lone pair counts as a place. Each of these bonds counts as a place. So that's 3 distinct places. So this would still be parent geometry of trigonal planar. I would still expect the bond angles to be about 120. So the bond angle between this H, this B, and this H is still going to be about 120. I'll talk about little perturbations to this in a moment. And that's it. I might not call this thing trigonal planar because there's no atom or no nucleus at the end of these electrons. I might call this thing bent. So if it's just 2 substituents that make it not a linear angle, I might call that bent. All right, for the next one, we could do ammonia. It's everybody's favorite. So this is ammonia. And we're going to start drawing stuff in 3D. So this is the Lewis structure for ammonia. How many places do I find electrons around the central atom? 4 places. I have a lone pair, and I have 3 distinct different single bonds. So 4 places total. That's going to be a parent geometry of tetrahedral. But look, one of the spaces is actually being occupied by electrons only. So I wouldn't call this a tetrahedron because the tetrahedron has 4 vertices, right? 4 points. So I would call this trigonal pyramidal, like a pyramid. Trigonal pyramidal. That's different than trigonal planar. Trigonal planar is flat. Trigonal pyramidal is actually a 3D shape. And I don't have it here. That's too bad. Might have to go back to PowerPoint. And let's see here. Come on, PowerPoint. Do you not exist in PowerPoint? I bet you do. I just don't have time to find you. Okay, so I'll try to draw it here. So we have this bond is just like a single bond like that. It means it's in the plane of the paper or in the plane of the board. This dash bond means that it's receding back from you behind the board. And this wedge bond means that it's coming out at you. I guess I should eventually do this stuff in 3D. Get you guys some glasses and stuff. But for now, you're stuck with this. So this is supposed to depict a 3D tripod-looking, pyramid-looking structure where the nitrogen is higher up than these 3 hydrogens that are equally low, and 2 of which are not in the plane of the board. This one's going behind the board. This one's going in front of the board. The wedge means going out of the board towards you. The dash means going away from you behind the plane of the board. Okay, what if we had water? So here's the Lewis structure for water. Oh, let me get rid of this boride thing. All right, so here's the structure for water. O, whoops, H, okay, how many places do you find electrons around water? 4 places. 2 places are bonds. 2 places are lone pairs. Right, these lone pairs. So that means what's its parent geometry going to be? right? I just looked down the chart. Tetrahedral, 4. So the parent geometry is tetrahedral. I'd expect, at least as a first approximation, that this bond angle is going to be 109.5. We'll talk about why that's not the case in a little bit. And we would expect to call it, there's going to be a different name for it because it doesn't have all of its coordination sites for the oxygen occupied by atoms. So the different name for this is going to be bent. So once again, if it's just two substituents that are not at a 180 degree angle, if there's a bend there, it's going to be called bent. So the parent geometry for water is tetrahedral, but the, I guess, structure that people assign to it, or the naming that they assign to it, is called bent, and that's how you get to bent from these considerations. There are two more, bless me, that I'd like to cover. The first one is Trigonal Bipyramidal. So if you have 5 elements around a thing, 5 places you find electrons around a central atom, you would, I'm doing my best here, guys. This is not working out very well. You would have a structure that looks like that. Let me introduce some 3D drawing to this so it looks better. And these different sites will have different angles. So I'm going to call these things A. Actually, that's bad. We'll call these things E for equatorial. And we're going to call these two sites A for axial. So the axial sites are at 90 degrees to all the equatorial sites. So all 3 of these equatorial elements are in a plane with the central element. And this A forms a 90 degree angle, like that would be a 90 degree angle, with the plane of these equatorial elements or substituents and the central atom. And in between these different equatorial substituents, there's an 120 degree angle. So this thing's a 90 degree angle, and this is a 120 degree angle. Octahedral is a little bit different. So for an octahedral structure, you get central atom, so all the sites are the same. You have 6 elements ordered around them, and every angle is 90 degrees. So the angle here is 90 degrees, 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 etc. Okay. I suppose there could be some naming conventions based on missing or sites occupied by lone pairs. If you had an equatorial position being filled by a lone pair, this kind of looks like a seesaw. Like these could be like the legs of the seesaw, and these could be like the kids on the seats of the seesaw. And this would be like the axis of the seesaw. So this thing's called seesaw. So it has like a seesaw structure. There are other names too. I think if you get rid of the A, like this, one of the axial ones, I think there's a name for that. I don't remember what it is. If you get rid of 2 opposite substituents here, you'd call it square planar. So this is square planar. So if I had like a lone pair here and a lone pair there, everything's still at a 90 degree angle, but now there's just a plane, so you call it square planar things. For doing the geometries, you can actually introduce a perturbation based on different relative sizes of things. So remember how I drew water and I was like, as a first approximation, we could say that it's got a 109.5 degree angle. Well, that's because it's not a 109 degree angle. If you have, like, let's look at water. Here's the Lewis structure for water again. If we were to look at the electron probability functions, the wave functions, the orbitals inside the molecule for this, you would see that there's a lot of electron density around where these bonds are, and they're kind of stretched out. I mean, like, these electrons are literally being shared between the hydrogen and the oxygen. So this is kind of telescoped out a little bit. These lone pair electrons, they spend all their time around the oxygen. So these are kind of like occupying more space around the sphere surrounding this oxygen nucleus. So because lone pairs aren't stretched out more, they end up taking a larger berth of angle, a larger slice of the coordination sphere around the oxygen. So as a result, they actually will hog some of the coordination sphere. So instead of this thing being 109.5 degrees, it's actually closer to 104. I think it's like 104.9 or something. Let's go look it up so I don't get this wrong. So according to Wikipedia, the bond angle between the hydrogens in water is, so the HOH angle is 104.45 degrees. So that's substantially lower or smaller than the 109.5 we started from the parent geometry of tetrahedral. So these lone pairs will actually take up more space than bonds will. If there's a multiple bond, it'll probably take up a little bit more space than if it's a single bond, because the elements in the multiple bond will be closer than the elements in the single bond. Larger elements will probably take up a little bit more space than smaller ones. But the biggest perturbation here is going to be that the lone pairs are going to take up more space than bonding electrons. And actually, lone pairs, if you just had like a single electron occupying a orbital, as what's an unpaired electron is called a radical. If you had a single radical in an orbital, that orbital would still actually be fatter, would take up more space than a bond would. So you should think of single bonds being the smallest thing, like the less greedy for angles and space around the central atom, and then after that, it's going to be it'll be multiply bonded, then it will be radicals, then it'll be lone pairs. Okay, so here we go. We have nitrogen. I gotta like draw. There we go. Pretend those are nicely drawn hashes. Okay. So here's nitrogen in ammonia. So tell me about this bond between the hydrogens and the nitrogen. So tell me about this bond angle, HNH. Is this going to be 109.5 degrees? Is it going to be smaller than 109.5? What do you think? Smaller. So we had water as an example. Those two lone pairs brought the bond angle down from 109.5 to 104.45. So what would your guess be for just one lone pair hogging more space around the nitrogen? Between those two numbers, right? So it's not going to be as much as 104.45, not 109.5. Who knows? Let's look it up. Usually the right answer is just look it up on Google or something, you know. And hang on, I gotta. Okay, so here's ammonia. I'd asked, hey, one lone pair, how much is it going to distort the parent geometry of tetrahedron from 109.5 degrees, knowing that water goes to 104.45 degrees with two lone pairs distorting it, and apparently it's in the middle, so 107.8 degrees for ammonia. Okay, so now we have a framework for figuring out geometries from Lewis structures. The final piece of this puzzle is figuring out whether or not the resulting molecule with that geometry is going to have an overall dipole moment. So this is kind of the last thing that I want you guys to be able to do from Lewis structures. And what does this mean? Let's look at ammonia. So ammonia has nitrogen and hydrogens. Nitrogen is more electronegative than hydrogen. Remember, if I go to the periodic table, here's nitrogen, here's hydrogen. If I was to look up the electronegativities, I'd find that things like nitrogen, oxygen, fluorine have higher electronegativities than hydrogen. So hydrogen doesn't have an electronegativity that's very different from carbon. So that's how I think about it. If I go to the structure and if I had to draw little dipole moments, and they're going to look ugly, and I apologize for that. Let me get a smaller line. If I was to draw little dipole moments parallel to these, I'm going to draw them on the bonds themselves. So there we go. So the arrows are always pointing towards the nitrogen. Okay. So all three of these dipole moments point from the hydrogens to the nitrogen. If I was to have like an overhead view of this, it would look like this. I'd have nitrogen in the middle, and I'd have these different hydrogens on the sides, you know, at the extremes. So here I'm looking down on the camera of the tripod, and here are the different legs that I'm looking down upon. This is all overhead view. I would see that the dipole moments all point to the nitrogen. And they do a better job than I'm drawing. They'd be symmetrical and not ugly looking. But I'm stuck here with my mouse, so you're stuck with that. So if I was to average all three of these dipole moments, what I end up getting is an overall dipole moment of that. Just a dipole moment that points straight up. So all the, if I was to call this the xy plane, all the xy directions of these vectors exactly cancel out, and all that's left is a z direction dipole moment. So an up-down dipole moment is all that's left when I average these out. If we go to water, and we think about what its Lewis structure and its geometry mean, so we said that this is what the structure for geometry for oxygen looks like, right? We said it was bent. It's not 180 degrees. So here we have dipole moments that look like this. Boom, boom. So this is going to have an overall dipole moment that looks like this. Water will have an overall dipole moment that looks like that. Water is more electronegative than the hydrogen, so it's going to have a partial negative charge. Each of the hydrogens is going to have a partial positive charge. And what I'm looking at here is an average dipole moment that comes from each of these individual dipole moments of the OH bond. So water is a polar molecule, which is great because it's responsible for us being alive. It's one of the very important properties of it. Okay, so that's water. Let's look at another one that's instructive because we did beryllium hydride. Let's do beryllium chloride. So here's beryllium chloride. What's more electronegative, chlorine or beryllium? Chlorine is more electronegative than beryllium. So both of these bonds are going to have dipole moments that point towards the beryllium. Point away from the beryllium. I made a huge mistake. They're going to have dipole moments that point towards the partial negative charge of the chlorine and away from the partial positive charge of the beryllium. Tell me about the geometry of this. What's the geometry of beryllium dichloride? It's going to be linear because there's two places you find electrons around the beryllium in these two bonds. So what's the bond angle going to be for beryllium dichloride? This is 180 degrees. Okay. So tell me, what's the overall dipole moment going to be when I have two dipoles that are exactly pointing in opposite directions and have exactly the same size? If this was like a tug of war, and I had two twin brothers with exactly the same training, two Lance Armstrongs with exactly the same, regiment of steroids and whatnot, pulling on opposite directions, would the tug of war, would there be a victor, or would it just be, static and nothing moves? They exactly cancel each other out. So this overall molecule has zero dipole moment. It is not a polar molecule. It is a non-polar molecule. It's not that it doesn't have dipoles, it's not that it has non-polar bonds. It's that its polar bonds lead to dipoles that exactly cancel each other out. So notice that we did everything the same between water and beryllium dichloride, except that we have a different geometry. We found that we had dipoles in water in the bonds, and we found that we had dipoles in the bonds of beryllium dichloride as well, or beryllium chloride as well. But guess what? Because the geometry is different, because the geometry of these dipoles in beryllium chloride point them away from each other, the overall dipole is 0. Whereas in this bent geometry, the overall dipole ended up being non-zero. It ended up making this thing a polar molecule. Okay, so with all these pieces in place, we can start doing brand new Lewis structures and going through examples that have just a formula, and we'll go all the way to polar, nonpolar for the whole molecule, which is pretty cool. Let's see here. Okay, so let's do the Lewis structure for boron trifluoride, BF3. And to do this, I am going to first look at the periodic table and figure out how many valence electrons boron and fluorine have. So if I look at the periodic table, boron is in this third column, like 13 column, or third column if you exclude the transition series. So it has 3 valence electrons. Fluorine has 7. So I can actually tabulate the electrons, the electron counts for this molecule. Okay, so what I can do is try to get the size of this thing right. Oh well. So each fluorine has 7 valence electrons. And notice I'm not talking about total electrons, I'm talking about valence electrons. So that means that there's 21 from each of these 3 fluorines. Each boron, there's only one of them, has 3 valence electrons. I'm not talking about the 5 total electrons, I'm talking about just the outer shell, the valence electrons that are available for bonding. So I can add up those 2 counts of valence electrons and see how many valence electrons total in the molecule are available for bonding. And the answer is 24. I can also figure out how many electrons those elements would like to have surrounding them. So these elements are in the second row. That means that they're going to shoot for an octet. They would be saturated by being surrounded by 8 electrons. So boron and fluorine both are in the second row, so they both obey the octet rule. And so each one wants to have 8 electrons. Since there are 3 fluorines, that's 24 total. So that's like, 3 times 8. So that gives me 24. And then boron wants 8 because there's one of them, so it's just 8. So overall, the molecule has 24 valence electrons, but it wants to have, or has, capacity to hold as much as like 32 electrons. So we can actually satisfy these octet rules by double counting valence electrons, or sharing them. So the difference between these two numbers, the amount that you have, the valence electrons that you have, versus the valence electrons you want to saturate the orbitals of the nuclei, it's just the difference of these two numbers. So, like if I have number wanted versus, so like bonding electrons is just the number wanted minus the number had, so that would be 32 minus 24. So there are going to be 8 bonding electrons. And if I want to count the number of bonds, well, how many electrons are in a bond? 2 electrons in a bond, so all I have to do is divide the number of bonding electrons by 2, and I will get 4 bonds. Yay. And I can do something even more clever. I could say how many electrons are not going to be in bonds, how many are going to be like in lone pairs or free radicals or something. I would subtract the total number of valence electrons we actually have, subtract from that the bonding electrons. So whatever electrons are not participating in bonding have to be participating in, or I guess not participating, non-bonding electrons. So I would expect that my final Lewis structure here is going to have 4 bonds. I'm getting this wrong. I have 3 bonds. What am I doing wrong here? I would expect from these calculations that I would get 4 bonds and 16 non-bonding electrons, but I have a feeling I'm making a huge mistake somewhere. So I guess the reason why we're not going to do this is because we're going to end up violating an octet rule. So let's find out. This is kind of an interesting one to start with. So boron trifluoride. So I'm just going to draw some valence electrons around it. This is sort of the Bob Ross version of how to do Lewis structures. And I know boron is going to be or I would guess that boron is going to be the central atom for a variety of reasons. The first reason is because the other elements are all the same, so I'm like, you know, if I have 3 fluorines and 1 boron and something's got to surround something else, I'm probably going to see the more unique element be surrounded by the less unique element. Additionally, I might also expect that I would see the more electropositive, the less electronegative element in the center as well. Boron is more electropositive. It's less electronegative than fluorine, so I'd expect it to be in the center. And finally, fluorine's got these 7 valence electrons around it, which means really once it shares one of its valence electrons and the valence electron of another element, it's basically done. I mean, once it has 1 bond, if I form a bond here, that's it. Now fluorine has a full octet. 2, 4, 6 non-bonding electrons and 2 bonding electrons from this bond. That's 8 electrons surrounding fluorine already. It's done. Fluorine's terminal for that reason. I mean, it's not going to be part of a chain because it can't really do any more bonding. So we also have, I can just keep drawing bonds here. So I could fill the octet of this fluorine by taking those 2 electrons I just erased and drawing them as a bond. And I could fill this fluorine's octet by, again, erasing these 2 electrons and drawing them as a bond. Okay. Now at this point, all of the fluorines are surrounded by 8 electrons, so they are all coordinatively saturated. They're done. Boron's not. So in this particular molecule, boron is not going to have a full octet. There aren't enough electrons to really do anything to get it to its octet. So there are occasionally molecules that don't have all of the octets of their nuclei, their elements satisfied. Sometimes you'll see this in aluminum, sometimes you'll see this in boron, sometimes you'll see it in beryllium. This just happens to be one example of this. I would guess that this well, we'll do some work with this molecule in a second, but I would guess that in real life, if I had a solution of this stuff in water or something, that the fact that this thing can accept electrons because it could add 2 more would actually make this thing what's called a Lewis acid. It could be an electron acceptor. So you might see temporary bonds from things that have lone pairs donating an electron pair to this boron. And I believe boron trifluoride is actually used as a Lewis acid a lot for that reason. Okay, so let's think about the geometry of this thing, and let's think about why my back of the envelope calculations were wrong. So they were wrong because we assumed here that boron would have a satisfied octet. It doesn't in this case. We ran out of electrons to use for bonding. So there we go. Now boron just has to suck it up with 6 electrons. Overall, the total number of valence electrons wanted and double counted between all the different centers would be 30. That means the number of bonds would be 3 and the number of non-bonding electrons would be 18. Let's just make sure that our Lewis structures is consistent with this and consistent with having 24 total valence electrons as a check. So just counting all the electrons, I got 2, 4, 6 electrons for each fluorine. There are 3 of them, so that's 18 non-bonding electrons and 3 bonds, so that's 6 bonding electrons. So that's 24 overall electrons, which is what we started with. So that's good that we did not invent or create or destroy any electrons. We're just changing how they're shared or where they're placed around the elements. And likewise, it's good that our non-bonding electrons and our number of bonds are consistent with accepting the fact that there's only going to be 6 electrons around this boron. In terms of geometry, how many places do you find electrons around the central atom? Who says 3? Who says 4? All right, so I had all of 1 vote for 3. That's correct. So each of those bonds is a place you find electrons around the central atom. So this thing is going to have a trigonal planar geometry. It's not actually as I wrote it. It's going to have 120 degrees between each FBF, friends best forever, I don't know. Every FBF bond is going to have a 120 degree angle. This thing is planar. It's trigonal planar. So if I was to draw all of these things correctly, there'd be like, just to crudely get this closer to what the geometry actually is, it would look more like this. And these all are very polar bonds. Which is more electronegative, fluorine or boron? Who says boron? Who says fluorine? Lots of people say fluorine. Great. So fluorine is more electronegative. That means that the fluorines are all going to have partial negative charges. So it's a covalently bonded molecule, but these are very polar covalent bonds. The electrons are not evenly shared. And the boron itself has a positive charge. A partial positive charge, I should say. And if I had to draw a dipole moment, I would just make these bonds look like that. The arrows point to where the electrons are more concentrated in the bond or where they're more likely to be found. Okay, so this is actually going to still be a nonpolar molecule because the geometry of this is trigonal planar. The trigonal planar geometry makes all of these bonds cancel each other out. The amount that this particular dipole moment is tugging that way is completely canceled out by the amount that these two are tugging in that direction opposite of it. So this is overall nonpolar, not because these bonds are nonpolar themselves, quite the opposite. It's nonpolar because the polar bonds exactly cancel each other out. Good? Okay. So that's how you do BF3. You would expect this to not have a dipole moment. The geometry is trigonal planar, and the boron does not actually get saturated or does not get satisfied in this case. Let's do N3 minus. Okay. So this is the azide ion, and we are going to go through and figure out the Lewis structure for this. So all the azide ion has is nitrogens. So how many valence electrons does nitrogen have? 7 or 5? 5, right. So 2 of the electrons around neutral nitrogen are in the inner core of electrons. The remaining 5 are the valence electrons, or the outer ones that are available for bonding. So for this molecule, we have 3 nitrogens, and we have a minus charge. So that's what that formula said. It was N3 minus. So each nitrogen has 5 valence electrons, and there are 3 of them, so that's overall 15. And the minus charge is just an extra electron. So overall, it's going to have 16 valence electrons that you'll see in the Lewis structure. But wait, there's more. So nitrogen's in that second row. It wants to have an octet, so it's going to have a capacity for, through sharing or other means, having as many as 8 electrons surrounding each nitrogen center. So that's going to be a total capacity of like 3 times 8. So it wants to have, each nitrogen wants to be surrounded by 8 electrons. So overall that's being surrounded by 24 total. So if you have 16 electrons and you want to get to 24 counted through bonding, what you're going to have to do is include 8 of those electrons in bonds, which means that the number of bonds that you need to have are 4, and we should have 8 non-bonding electrons. Let's check this out. So let's draw some nitrogens, surrounding them by 5 valence electrons. Here, so that's 15 electrons. Did I forget anything? I got the N3. What about the minus? So what do I have to do to depict that minus in terms of a Lewis structure? I have to add another dot. I have to add another electron. So I'm just going to add an electron here. So now if I count this, I should have the right number of electrons. 5, 5, and 6. So that is 16. Let's go back to my tally. And okay, so at least so far, the right number of electrons. As I start making bonds and figuring out whether or not octets are filled and stuff, I might actually accidentally erase some. So I will always come back and just kind of like recount, make sure I got it right. Okay, so right now this thing's surrounded by 5 electrons, 5 electrons, 6 electrons. Guess what? They want to have 8. That means we can do some bonding to increase the sharing, and no one's octet's filled yet, so I can just add a couple bonds and see what happens. All right, so let's share those 2 electrons. This is going to be ugly looking, but so be it. Let's share those 2 electrons. Bam. So I either write over or I erase the electrons that I'm that were lone parallel non-bonding electrons that I'm turning into bonding electrons, just to keep the counts right. Okay, so now this one has 7 electrons. This one has 3 and 2 and 2, so that's 7 electrons, and this one has 6. So why don't I draw another bond here? Why not? So let's erase that, and we'll draw a bond from those 2 erased non-bonding electrons. So now this one has 2, 4, 6, 8 electrons surrounding it, so this one is now done. We might have to do some changes later, but let's just call it done for now. How many electrons does this nitrogen have around it? How many bonds surround this nitrogen? I'm asking for literally Sesame Street style counting right now. 1, 2, 3, right? Boom. Now, I multiply that by 2. That's going to be 6 electrons in those bonds. And I also have these 2 up here, so that's going to be 8 total. Okay. You guys are like bored and you're like, why are you asking me these questions? They're so stupid. Okay. So this one's also done. How about this one? 1, 2, 3, 4 non-bonding electrons, and this bond means 2 bonding electrons, so that's 6. This one's not done. This one needs more electrons. How do I increase the number of electrons to this nitrogen on the end without depleting the number of electrons around this one? Yes. So this one, without losing these electrons, could just share those electrons. All right, boom. So there we go. All right, so now this nitrogen still has 4 times 2 is 8 electrons around it. But this nitrogen is now saturated. It's now satisfied with 8 electrons in its octet. So at this point, we would say that this Lewis structure looks good because we have 3 nitrogens with satisfied octets. We have, I said we'd have, well, let's count. We have 1, 2, 3, 4 bonds, and we have 2, 4, 6, 8 non-bonding electrons. 8 non-bonding electrons, 4 bonds. So that looks good to me. I'm not sure if you're required for it for this course, but if you need to write this for a future course, make sure, number one, that your electrons that aren't bonding are paired up. That's good form. Also, you should draw formal charges. So nitrogen starts with 5 valence electrons. And if you wanted to, for accounting purposes, you could actually try to figure out how many electrons are surrounding this nitrogen if you just split each bond in half. So this is like 2 bonding electrons, 2 bonding electrons, so that's 4 bonding electrons total. If we were to say, okay, I'm going to account for half of those 4 electrons going to this nitrogen, that would mean that this nitrogen has 2, 4, and then the 2 split from the bonds, 6 total electrons. Nitrogen starts with 5 electrons, so it has an additional electron, so it has a minus charge on it for 1 extra electron. Nitrogen starts with 5 electrons. If you split these 8 bonding electrons and you try to assign a formal charge to nitrogen, giving it half of these 8 bonding electrons would give it 4 electrons. Nitrogen starts with 5, so that's 1 less electron, so that would be a positive charge for nitrogen. We've depleted neutral nitrogen by 1 electron, so we give it a positive charge. And over here it's going to be the same thing as this one, right? Symmetrically, it's the same thing, right? Same situation. 2 bonds, 4 electrons that get split between these 2 nitrogens, so that's 2 electrons to this nitrogen, and then 4 non-bonding ones to this nitrogen, so that's 6 electrons. It started with 5 valence electrons, so guess what? This is a minus charge assigned to it, no longer neutral nitrogen, we would assign a negative charge. Overall, this ion is an ion. It has an overall charge because we have a -1 charge here, a plus charge here, and a minus charge there. So 2 minus charges, 1 plus charge. Overall, this thing has a minus charge. So we actually wrote a good structure for this because we, 1, satisfied all the octets, 2, have the right number of electrons that did not screw up the actual charge we started with, and 3, we just didn't do anything crazy. We don't have more than 8 electrons surrounding any of these nitrogens. It's all consistent. Okay, so that's my last example.